Hello and welcome to another episode of Carbohydrate discussion series. Today, Deepak will present stereoselective construction of Sialyl linkages. Enjoy the session.
Good morning, everyone. So today we'll discuss this paper which came in Engu Chemie in 2019. 1 pico linyl 5-thiosialosides, which is a versatile donor for the stereoselective construction of sialyl linkages. So what they have done, they have taken this picolyl group at the C1 position and then HDO group at the C5 position, this donor, and they will be using this donor for the glycosylation. So as we know that in sialic acid glycosylation, still there are very few glycosyl donors are there which can be used in general glycosylation for sialic acid, which can give some stereoselective product. So why there is always problem with the sialic acid donors are there? So few key challenges are there. The first one is the presence of the electron withdrawing carboxylic group at the anomeric position, which always reduce the reactivity, and same time the tertiary nature of the anomeric center and absence of this C3 hydroxy group, which not only result in the low stereoselectivity, but because of this always there will be the competition for the formation of elimination side product. So to address all these issues, there are few key approaches are there. First is that the people used to use different solvent system, like some participating solvent or something, which will reduce this issue. And other than that, some novel leaving group can be used, which can be activated in some particular fashion. So these problems of elimination and stereoselectivity can be solved. Other than that, people has always also come up with the new kind of protecting group or some participating group. Moving further from that, another change we can do is that acceptor nucleophilicity also play a significant role. So if acceptor nucleophilicity can be changed or some protecting group at the C5 position, that pattern will change. All these are the key factors which can give the some different stereoselective. It will help to form the stereoselective product and reduce the elimination product. So in this paper, why they have chose C5 azido group and then this C1 picolyl group. So to select the picolyl group, the direct evidence is that it can participate directly towards it can act as a neighboring group, participating group, and same time C5H2 group. Mainly, the first point is that they have taken it can be modified after glycosylation or silation, so it can help in the post silation modification. So it can facilitate to couple with the various other psilocybin and some another moiety. Another well-known fact which is already there in literature that C5H2 group alone, like it cannot alone control the efficiency of glycosylation, but its strong electron withdrawing effect can be exploited to strengthen the participating of the incorporated like this group. In coherence with this electron withdrawing group effect of the N3, it can be utilized both together. So coming to this work, what they have done, they have synthesized this donor 2 using this Sialyl glycoside 1, thioglycoside they have taken. Then they have treated with the lithium chloride in PD, reflect condition for 24 hours. So that will remove this methyl group to acid, and then this can be coupled with the picolyl bromide in the basic condition to form this donor 2. So once they have this donor 2, it will be in alpha beta both isomers are there. So once they have taken this model reaction for optimization. So they have taken this acceptor. So once when they are treating this beta donor of this glycoside and they are taking 0.2 equivalent of triplic acid, they are getting very less yield of this corresponding disaccharide, but stereoselectivity is very much good, 25:1 alpha selective product they are getting. The moment they are increasing from 0.5 to 1 equivalent of triplic acid, they are getting excellent yield of the disaccharide and keeping the stereoselectivity is still very much good. So as the equivalent of triplic acid is increased, the formation of corresponding disaccharide has been increased. And same time when they are taking alpha glycoside, still the formation of product is little less, but the stereoselectivity is almost there only. And from this reaction, they have also shown that the reactivity of alpha glycoside is more than the beta glycoside. For the conversion of this reaction, alpha from alpha donor, there it is getting converted into 1 hour. But for when they are taking this beta donor as an donor, it is the complete reaction conversion is happening after 2 hours only. So from where once they have optimized condition in hand, they have explored the substrate scope. For that, first they have used the various primary acceptors. So starting from this very simple benzyl alcohol, in that case also they are getting almost 88% of yield and keeping alpha beta ratio to 20:1. But in the case of this another acceptor, again they are getting alpha selective product only, but the reactivity is little lower if this OBN or group can be substituted with OBZ. Like if you'll see in this case, acceptor is having two OBZ group, C2 and C3. In that case, they have got 78% of alpha selective product, but they are once this conversion is happening only when they are increasing the temperature from -40 to -20. At -40, this reaction is very sluggish. So once they are increasing the temperature from -40 to -20 or to -10 gradually, they are getting better yield and better selectivity. But it shows that the reactivity of this acceptor is little lesser. Same time when it is OBN protected, they are getting at -40 degrees Celsius only, they are getting 83% of yield. Similarly, when they are getting the C2 azido acceptor that is well known to reduce the reactivity of acceptor, in that case also they have got the good selectivity. And in another case where they have given idophenyl group at the anomeric position, this they have kept it deliberately, that we'll discuss later. So in these kind of cases also they are getting the alpha selective product. So in all this primary acceptor case, they have got the good yield. So when they are coming to the secondary or tertiary acceptors, which is known to react very slowly, or in case of sialic acid, it is difficult to get the glycosylation with the either secondary or tertiary acceptors. So in their case, they have started with the first very simple cyclohexanol. In that case, in their donor, they are getting the good yield of glycoside at -40 degrees Celsius. But when they are doing it admentanol, that time there still the stereoselectivity is good, but yield of the reaction is getting reduced to 50%. And same time they have increased the temperature from -40 to -22, and finally they have increased to the 0 degree centigrade also. Then only the conversion is happening. And when they are taking this C3 hydroxyl acceptor, in that case also, in previous literature, it is known to give very less stereoselectivity and yield, but in this work, they have shown that C3OH also can give very good amount of yield and completely stereoselective product. So one in another case, still what they are saying in this case, yield is little lesser and selectivity or reactivity little relatively slow, but when they are changing this protecting group from OBN to this main lean protected acceptor, in that case, they are getting the better yield of having C3 acceptor. Once this R group is again, if C2 group has been changed to the azide group, again this reactivity is little lesser. So in that case, they have to increase the temperature to minus 20 degrees centigrade. So similarly, with various secondary acceptor, most of the time they have to perform the reaction at little higher temperature than minus 40 degree. So which will be either minus 20 or 0 degrees centigrade, then they are getting. But most of the time, selectivity is alpha only. To check the L series of sugar, they have taken L rhamnose and having C4 free hydroxy group. In that case, they have got the good amount of field, but its selectivity is very much less in this case. Still, it is alpha favored, but they are getting only 3:1 selectivity for alpha is to beta. So once they have performed this, another challenge they have taken that to synthesize the 2,9 or 2,8 linkages of the sialoside, taking two sialic acid and couple to form the sialic acid disaccharide. So it is known to be very less reactive and very difficult to form because the nucleophilicity of this C8 hydroxyl group and C9 hydroxyl group is very less. But in their case, they have got, once they are starting, they have taken this donor 2, and when they have coupled with this acceptor, keeping both hydroxy group C8 and C9, both hydroxy group free at minus 40 degrees centigrade, they have got the 82% of this disaccharide 37, keeping this one of the hydroxy group is not reacting. But in another case, if they are protecting this C9 hydroxyl group and only C4 C8 hydroxyl group is free, in that case they have got the 52% of this desired glycoside, and rest of the starting material is remain unreacted. So if they will calculate the yield based on the uh, remaining starting material, in that case they are getting the yield to 90%. It means whatever the amount is getting reacted, almost it getting converted to the desired product only. And in both cases, they have got exclusively alpha selective product. So once they have shown the substrate scope of primary, secondary, tertiary alcohol, and then they have coupled this sialic acid acceptors also. Further, they have shown the this selective. Once the donor is formed, then selectively picolyl group can be cleaved or not. For that, they have used this copper diacetate 1.1 equivalent, and they have used only methanol. Like earlier, it is known to be, this reaction is known to be done in methanol dichloromethane condition to give the selective deprotection. But in this case, once they are using this methanol at 45 to 50 degrees Celsius, that case, mm, in that case, they are selecting, they are able to get the OMA substituted and piconyle removed, donor 39 to 44. So once they have done this, again the next target they have taken that the after silation, how they are able to modify this azide moiety. So they taken this thiostic acid and pyridine at room temperature, and they are able to selectively transform this azide to NHSC, and similarly in this case also, which contain the cyadophenyl group, in that case also they are able to transform to azide to NHSC moiety. And later in these cases also, when they are taking this pyridine and piperidine, and then they are able to substitute this in case in place of NHSC, they are able to form this benzyl amide substituted substrate in this case also. So later this can be used in some another kind of tagging or something. This uh, agent can be used. So here they are trying to show the this azide can be modified after the glycosylation. So once they have done that, so next what they have targeted the synthesized type 1 antenna and type 2 antenna molecules using latent active strategy. So for that, what they have done that they have taken this donor 2 and they have coupled with this acceptor which contains C6 hydroxy group and at numeric position idophenyl group they are keeping. So once they have coupled in their optimized condition in NIS acid, so they are able to get the 90% of this product, and then this N3 group they have transformed to the corresponding NHAC, and same time they have reduced this picolyl group to transform this picolyl to AME using this previously optimized condition, which is copper diacetate in methanol 45 degree to 50 degree centigrade. And after that, what they are doing from the same group, they have previously developed one donor, which is paramethoxy, paramethoxy, orthoparamethoxy kind of donor, some donor. So that they have last year they have published in JSES. So that same donor, that's why they are keeping this idophenyl group, and later they are coupling with this ethylene alkenyl moiety, that paraphenyl alkenyl moiety in the presence of palladium catalyst and copper iodide. So they are transforming it to the orthogonal OMPEP donor, and then for that again, like this is the latent active donor they are talking about. So this is the previously developed donor from the same group. So once they are coupling this sialic acid to one of their donor, and then later they are modifying just this position. So again, this is the latent form of donor. They will make it to the active form of donor. Then in the presence of NIS triflic acid and 300-watt light condition, they are transforming, and they will couple again another acceptor which is having the latent form of their donor, and again they will able to transform it to the active form of donor, and again they are doing another coupling and so on, so they can form the tetrasaccharide. Or if they want to increase the oligosaccharide length, it's still they can do that. So all these things they are doing after the stylation in the first step, and later they are doing glycosylation from their old glycosylation method. So similarly, this is the type 1 antenna molecule in which this C6 OH is getting coupled. In another case, this secondary hydroxyl group is coupled. In this case also, they are starting from this first substrate, which is having two free hydroxy group. In that case, once after the coupling, only the C3 hydroxy group is getting coupled, and after that they are they are doing this benzoyl protection in pyridine, and then again they are removing this picolyl group to OMe, and they are and then again transforming this azide to NHAC, and then they are following similar setup sequence which they have performed earlier, no, based on their old donor. So later glycosylation, they are not doing silation, they are doing glycosylation using their old glycosylation method to form this tetrasaccharide. So once they have done this, to the next they have taken the challenge to show the stereodirecting effect of the picolyl group, whether there is some stereodirecting group of picolyl group is there or not. So for that they have taken this acceptors 3, 5, 7, and so once, and they have taken this donor. So what they were observing, when picolyl group is there, in that case of glycosylation they are getting 25:1 selectivity, but the moment R group they are changing from picolyl to methyl, in that case they are observing only very less alpha to beta selectivity. Similarly, in the case of this simple benzyl acceptor also, in the case of picolyl group, 20:1 selectivity is there, but the moment picolyl group is changed to methyl, the selectivity is getting reduced. So, and in case of this OBN protected acceptor, in that case also, again, in that case, they are getting alpha selectivity only, but the moment picolyl group is changed to the methyl group, in that case the selectivity is reduced drastically. So it means that some role of picolyl group is definitely there, but how exactly that role is there? For that, they have given the possible mechanism responsible for the excellent stereoselectivity. So they have proposed that these three possibilities could be there. First one could be there, this picolyl group directly it can stabilize, it can form this kind of intermediate, and then after SN2 substitution, it may lead to the formation of SN2 product. Other than that, there is another possibility. This picolyl group can indirectly by taking this proton and it can stabilize this intermediate 4, triplet intermediate 4, and again after SN2 substitution, it may give to the formation of this SN alpha selective product. Other than that, another possibility is that this this intermediate, like this only picolyl group can form this kind of intermediate, and just after in triflic acid, just after triflic acid equilibrium, it may form this kind of triplet based intermediate, and again it will lead to the formation of SN2 substituted product. So how exactly it is happening? For that they have done the various control experiment, and they have some they have removed, they have changed the sequence of addition and of NIS triflic acid, and they have used different equivalent of promoters also, some different promoters also. They have done lot of optimization, and they have done some computational studies also. Based on that, they are proposing that this intermediate for beta prime, which is having very lower in energy in comparison to the other donors, other proposed intermediates. So if you check this one in this case, like this is the very much favorable intermediate, and based on this experimental investigation and computational investigation, they are proposing that this intermediate will be very much stable, and most probably this is the case after SN2 substitution, they are getting the alpha selective product. Other than that, they have done this reaction in the gram scale also. In the gram scale, when they are doing it into the 1.6 gram scale, still the selectivity is very much alpha selective product they are getting. And when they are performing at room temperature, in that case also, they are getting the alpha selective product. Thank you.
Uh,
Yes.
Nice presentation. Can you go to the, means you keep on going, maybe in one of the glycosylation? This one. The four, slide number 4. If you see here, the reaction with the 35 acceptor, so it has both primary and secondary OH. So based on maybe reactivity, we may think like secondary for primary is reacting rather than secondary. So that's what happened here.
Yes.
So in that case, why did they protect other secondary alcohol then? Because it is quite more number of step to get that selective protection.
Other secondary means what? These
This
things.
C4 and C4OH and I think that is C7OH.
No, no, then in that case also there are few very old reports are there. In this case, why they have done? Most likely this starting material, how they are making, they will selectively protect this, and
Uh,
other protecting groups are already there. So this, what is that? Not
Acetonide or
benzoyl.
something like that.
Estonide, yes. Estonide means dimethyl.
And
Uh,
SS propane. That one.
Propane
Got
dimethyl
it.
protecting group is there. So they are doing just one D protection, and they will be able to get this. And already if there will be more deprotecting group, means more free OH are there, there is a
Uh,
possibility always you will get some kind of regioisomer you may get. But in this case, since these two are very less nucleophilic, it is very much known that to get this
uh,
disaccharide, it is very difficult, as it is claimed in many previous literature reports. But
uh,
in these two, obviously, this will be more nucleophilic, more nucleophilic. That's why they are getting the selective this primary OH substituted product only. And once they want to get this secondary OH substituted, in that case, they are forcing it to go with only this acceptor. That's why in this case, yield is also very less. Yield means only very less reactivity is there. Some most of the starting material is remain as it is.
So and again also like the role of N3 here. So is it
Yes.
like that much necessary to convert from NH?
So in beginning only they have told that it is not that much necessary, but based on this energy and whatever the
Okay.
mechanism they are proposing, they are saying it could have some role based on this whatever mechanism.
Electron withdrawing nature.
Yes, so it is somehow it is able to stabilize this kind of
Mm.
intermediate, this and this two, whatever they. I didn't get it completely how actually this is happening, but they are proposing that it can play some role. So they are
Mm.
not exclusively saying that it definitely achieve. Their main role is to keep N3 is that to do the post glycosylation modification. So if N3 is
Okay.
there, they can do lot of modification after glycosylation. If you will see
Mm.
these two syntheses, we may not feel too much about it because they are doing glycosylation in first step. After that, completely different glycosylation steps are there. There is no role of silation. So
Okay.
somehow there the point is that once, because most of the time in natural substrate sialic acid is in the terminal position, so there
True.
is
True.
no harm keeping the sialic acid in first uh, step itself, and you do later modification to get the whatever oligosaccharide you want to get
Uh-huh.
tetrahexa.
And on top of that, also people have if you wanted some add some adjuvant or again something
Yes,
like that. So that is one of the linking point. There are too many reports that have changed the NH group and they have studied the effect or the better the react better the result and
yes.
all. And
So
also
they,
uh,
yes, go ahead.
so so the mechanism, so here also like if you see even whether it is this donor or whatever the donor, ultimately should go in similar fashion only. So only maybe because of the energy DFT that whatever that picole is there, that
Yes.
might be creating little less energy for
Ah, yes, that
this
possibility is
glycosyl.
there. So in mechanism also they have done lot of control experiment. It was little
Uh,
difficult for me to converge, but the main conclusion is that only it has some role and it is forming this kind of intermediate, either this or this one, which is having lesser energy. So they are
mm,
thinking like if you'll see byproduct, any way is fine. It can
yes,
go
yes,
via
yes.
any way, any pathway. It is
Mm,
giving same product only. Just
uh,
to elaborate it more, they have proposed the different possibility whether this protonation is helping or just this picolyl group is helping. So based on that, they are suggesting that this pathway is more favorable where this intermediate after protonation it is somehow it is stabilizing this triplet, and same time this uh, electron withdrawing nature of N3 is also playing some
mm,
role to stabilize this triplet in this intermediate.
okay. So this is center cleavage. And again, what are the thing I see also? So what does that? I forgot actually that deprotection of that people group.
This,
So it is copper diastrate, right? So
yes,
usually, what if you use methyl ester or something, we need some strong base like sodium hydroxide or potassium hydroxide. So that is one of the advantage here. You need a mild condition like copper state just to deprotect it. And again, they have protected in methanol condition. Okay, this side in terms of.
yes. So actually, what the thing is that acetate is there. So
Uh,
already it is not known that in the presence of BZ or acetate, picolyl group selectively can be
Uh,
removed in the presence of copper diacetate in dichloromethane and methanol. So that they
okay.
have attempted first. So in that
Uh,
case, some problem was there. So they were not able to get the conversion. So they have just used methanol. So this is already previously reported reaction where picolyl will be removed in the presence of other esters selectively.
okay. So they removed and again they methylated it.
The dichloromethane methanol mixture. So methanol in that itself, methanol itself, it is going there.
So is there any in the substrate scope or is in the synthetic utility? They have deprotected all the groups. I didn't see anything like that, if I'm not wrong.
No,
Right?
no, they are doing this selective deprotection. So wherever required, like in some of the case, this N3 modification or picolyl modification as per requirement, not complete deprotection. Like if you'll see here also, so here they are transforming as per requirement. Like later when they don't need picolyl group and this N3, they have removed
Okay.
and then they are doing further glycosylations.
Okay. Okay. And what is this?
So it's
It- Something AW 300 molecules is.
and that is something I didn't check their old paper.
Okay.
So
Okay.
right now I don't
Because there are a
remember.
lot of new
But this
terminology
paper
we could
came, I
see.
guess, 2 year back it came. Last to last year or
2019,
last
na?
year it came.
No,
Uh,
no, it is 2019
okay.
paper.
Okay, then it may be even more older paper, but this donor they have established earlier. This came in JACS, so they
Okay.
have worked a lot on this donor. So this is very much established donor. So that only they are
Okay.
using.
I think this is something like that only you need some copper or gold catalysis because
No,
that
no,
has
no. It is
alkynyl group, right?
no. It is based on. Ah, okay, okay. Maybe I don't remember, but I remember maybe gold or some protonation of this methyl, and then
Uh,
somehow this it is getting shifted. The aromaticity is
okay.
changing, and then that group will leave. So two methyl groups are there. Para-methoxy group has some role there.
Hmm.
Okay, I don't remember
Okay.
exactly, but this they have
Uh,
reported very much earlier. This is very much worked out donor.
and also in the many of the substrate, it is like they use the because it is too much of a substrate scope, right? I think whatever
Yes.
they were used earlier and prepared and kept, they might have used here. Like since you are doing like this no, nowadays,
Ah, yes, that
so
possibility is always there.
uh, so this is what happens. And if you go to any of the where the picoline has been structure is shown properly, any of the previous slide or earlier slide. If you see here, like I don't know how much right I am. How we do the hydrogen analysis, right?
Yes.
That is ultimately cleavage of the heteroatom at the benzyl deposition. So my out of curiosity question is, can that happen here also?
I don't think so. You are saying this
Because it is.
bond cleavage, like
Yes, yes, yes,
hydrogen.
yes, 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 yes. I don't know that. I just had a doubt, so that's why I asked.
In that case, I don't know what happened to this thio and other thing. And three is also there in same case.
But
That
in
will
that
also.
Here,
case,
here
acid will
definitely, here
form.
definitely.
In that case, acid is formed and CO2 also
No, no,
gone.
that's see here. There is no reason of doing that one here because there are a lot of other things are there. We can't do here.
Yes.
Just I am just randomly asking that if that kind of a group is there, does this benz hydrogen analysis works here or what?
Hydrogenolysis
I
is
think it
possible.
will
It
work.
will work.
It
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 will work.
may have to couple with other thing. Like if you see here also, this you may have studied like Krebsco methylation something. So they will form this
Okay.
acid and then this
Uh,
acid they are using further. So in other steps they are
okay.
simultaneously they are changing this acid.
So this step means your lithium chloride can cleave the methyl ester.
Yes, this is textbook reaction if I remember correctly. Krebsco
I have seen lithium
demethylation.
hydroxide, I have seen potassium hydroxide, I have seen sodium hydroxide while studying for my sialic acid, but I didn't see this lithium chloride. Okay.
I
Decided.
don't remember very much, but I think this is some textbook reaction is there. We have studied.
Yeah. And
So
also in
this will
optimization.
this will form acid, and then acid they are using to couple with this picolyl bromide.
Okay, okay. That is just uh, highlights and that's fine. That I understood. Like and also in optimization also it is like very much obvious that you need a stoichiometric amount of tryptilic acid rather than catalytic amount.
Okay. Why it is obvious?
No, no, not maybe I misspelled
Because
it.
most of the
When
thiodonors
no,
they
no,
are
no.
using very lesser equivalent of tryptilic
But
acid, right?
here the optimization shows you need stoichiometric amount, na?
Yeah, here it shows, but you are saying it is very much obvious.
No, no,
That's
no.
what.
Maybe I misspelled it. Like this visible here that you need to use I,
They are showing that the moment
uh,
they are increasing from 0.2, 0.5 to 1, they are increasing the yield. But other
what
than
are the
this, if
subsequent
you see
reaction they
the
used
old, what subsequent reaction?
means like which substrate scope or synthesis and all, they used catalytic amount only or the stoichiometric
No,
amount.
no, they are using this one equivalent only everywhere.
Okay, okay.
So that they are not changing. Only the
Uh,
thing they are changing the temperature and all the
mm,
substrate. So it's kind of you have to do optimization at every step, like based on the acceptor every time. They are changing little bit. So it's not
okay.
like only one, the generality is limited. So that is everywhere in all
Uh,
the sialic acid cases, that is the major problem we have, right?
okay. Okay,
So
yes,
there
yes,
is
yes, yes.
no very much general glycosylation method like TCA.
True,
You take
true,
any
true,
acceptor and you do that. So
true.
in these cases, still that limitation is there. They are claiming
Uh,
that they have removed it to maximum extent, but in their substrate scope itself, you will see in most of the time, sometime they are doing -40, -20, even they are doing 0 degree and room temperature also.
uh, so first of all, I think I missed the point. Why I asked about N3 role in the beginning itself. Like if you see whatever the work you are doing, that has a little quite different than other. Like you have BZOAC.
Yes.
So I just thought of asking, but I missed it. Like how you correlate with B because here they are different because of electron withdrawing, some has rows. So in that your case also your BZ in with the NBZ and AC that might be having some role. What did you observe when you just tried with NHAC and what NBZ and AC?
So based on this work, what I feel now is that it has simultaneous role of both the participation is also there and electron withdrawing effect is even enhancing the selectivity.
Okay.
So
Okay. And
that what
in
I
your
feel
case,
that
yes, sir.
OBZ group has the
Uh,
some direct participation is there, like neighboring group
yes,
participation is
yes,
there in
yes, 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 yes.
selectivity.
Yes, yes, yes.
That we cannot correlate with this
Uh,
work, but some already in this work also they have mentioned the
mm,
previously those kinds of reports are there. The
mm.
pattern of substitution having some role in the stereoselectivity.
Okay. So why? Because like if you see our accessory also, so that has a like NGP kind of a thing, the like distant participation. So like that, in your case, the BZ might be having, as you are telling, it might be having some role. So that's why. Did you
Yeah.
feel any difference in selectivity when you're doing with NBZ and AC or NHAC? Did you do any control
That I
experiment like that?
haven't done yet.
Okay, so that may give you the idea whether BZ is
Yes,
literally involving it because that is something very different we don't see in normal paper. That might be
yes,
one good point. Like the moment you keep BZ there, so you might be increasing the selectivity. So that might be good add on to the thing.
yes, correct.
Okay, thank you.
If you enjoyed this session, don't forget to like, share, and subscribe. We'll meet you in the next episode, next session. Thanks for watching.